Hey, Mr. Fusco here. The question we're looking at right here is a combination basically of electrical forces, gravitational forces, and tension forces. Now what I'd like you to do before you watch this video, please try this problem on your own. So pause the video now if you haven't tried it and do your best. Unpause the video if you need some help. Okay, so let's get started. So for part A, all it's asking us to do is draw a free body diagram and show all the forces that are applied onto ball C. Okay? So before we do that, let's just make sure we understand the problem. We have two identical balls, B and C, so they're the same in mass, both half a gram, and they're suspended from two strings as shown above. Both balls have an electric charge of 10 nanocoulombs and are separated by a distance of 4 centimeters. So between them here, that's a 4 centimeter difference, okay, or distance. All right, so let's just get the free body diagram out of the way first. So it says draw a free body diagram and show the forces on ball C. So ball C, I'll just draw that right here. Okay, well, we're going to assume that we're on planet Earth, and ball C is going to be subject to the force of gravity, which I am just going to write down as mg, the mass of that object times the gravitational acceleration. Okay, now there's more at play than just the gravitational force. We also have the fact that these two balls are electrically charged, right? So we have to ask the question, are they going to repel or attract each other? Well, if they're the same charge, then they have to repel, okay? So we have ball B above ball C, which means that the electrical force on ball C from ball B is going to have to point downwards with gravity. So I'm just going to write that there. That's my electrical force. All right, so we've accounted for the weight or the gravitational force of ball C. We've accounted for the electrical repulsion from ball B on ball C. But we also have another force, since it's tied to the string, and it says it's suspended, which means it's in equilibrium, right? It's not moving, it's just suspended there. Oh, and by the way, since we know it's suspended, it's in equilibrium, that means the acceleration of the object, at least in the y direction, is going to be equal to 0 meters per second squared. We know it's in equilibrium, so that's an important thing to establish that we understand, okay? And if we know the acceleration is 0, that would mean that there has to be another force that cancels these other two out. And when we know what that force is, it's tied to the string, so it's going to be tension. Now I'm going to draw this tension force large enough, again not exact, but just so you get the picture that this force should be able to cancel out both of these other two. So we'll have the tension force able to cancel out both the electric force and gravitational force. Okay, one thing I'm going to do with this question, just to make things absolutely clear, I'm actually going to rewrite Ft. I'm going to rewrite it as just capital letter T. We know this is still a force, okay? I'm writing capital letter T, but it's still a force. And we know it's the tension on string between ball C and B. I'm going to call it TBC. Now the BC means it's the tension from ball B on ball C, okay? So that's what we're going to abbreviate it as. Now I know it's the letter T, but still remember it is still a force which is measured in newtons. Okay, that is our free body diagram. We know all three of those forces should cancel out and give us an acceleration of 0 because it's suspended from the string. It's in equilibrium. That's part A. Good. Once you have that, we can now try to go to part B, which is to actually find the tension force in string BC. So that would be actually to find this TBC right here. Now this is the part where a student will always ask me, oh, Mr. Fusco, what's the equation for tension force? And I'll respond, there isn't one, okay? You have to find out tension force in the context of all the other forces that are on the object. And the way we do that is with Newton's second law. sigma F equals ma, right? Now in this case, it's all in the everything in this problem is in the y direction. So I'll say sigma Fy is equal to ma in the y direction. Now if you remember what we mentioned earlier, we said that in the y direction, the acceleration of this object, since it's suspended, the acceleration is going to be 0 meters per second squared, which means that sigma Fy equals 0. Okay, so we know that all the forces in the y direction have to add up to 0. Let's go ahead and start trying to add up all these forces. That's sigma. We're going to add up all those forces. So let's first start with the forces that are pointing upwards. We'll consider those the positive forces, and we'll consider the forces that are pointing downward the negative forces. So pointing upwards, we have tension of B on C. Okay, so TBC is positive. And then pointing downwards, we have the electrical force minus Fe. Also pointing downwards, we have the gravitational force minus mg, all equal to 0, because again, it's an equilibrium. Okay, this is our setup. This is the most important stuff here. Everything up until this point is really the stuff I'm worried about you understanding. The next part of this one is just simple algebra. Just find the tension force in string BC. To do so, all we're going to do is solve for BC. We'll isolate TBC by adding Fe to both sides and adding mg to both sides. So TBC equals Fe plus mg. Okay, now to actually calculate the tension of B on C, we need to know the mass of the object, gravity's acceleration. We know the mass of the object, that's 0.5 grams. We know gravity, that's going to be 9.81 meters per second squared. We don't know the electrical force, so we're going to have to calculate it. But what I'd like to do for our next step is, instead of plugging numbers in just yet, I'm actually going to plug in the equation for electric force. So we remember, the electrical force can be found K Q1 times Q2 all over the distance between the charges R squared plus mg. Alright. Now, we could simplify this a little further because we know both the charges are the same. So I could rewrite this as TBC equals K Q squared, because both Q's are the same, all over R squared plus mg. Now it's just a matter of calculating. Remember, the electric constant is 9 times 10 to the 9. The charge of both these objects is 10 nanocoulombs. And we want to make sure we plug those in terms of regular coulombs, not nanocoulombs. So remember, nano is times 10 to the minus 9. I always remember that nano. That's my little mnemonic device I use. 10 to the minus 9 all over the distance between them, which I believe that was 4 centimeters. So remember to convert that to meters. 0.04. Square that, plus the mass, which is 5 grams, 0.5 grams, which you must convert into kilograms. So that becomes 0.005 times 9.81. Okay, those are all our numbers, and once you calculate that, you will find that it's 5.47 times 10 to the minus 3 newtons. And if you really wanted to, which I do, let's write that as 5.47. Now we know 10 to the minus 3 is a millinewton. So our final answer for part B is the tension between B and C is 5.47 millinewtons. Okay, moving on. Okay, part C. Draw a free body diagram and show all forces that are applied on ball B. Alright, so here's my ball B right there. Now again, we're going to assume that we are on planet Earth. So we're going to have the weight, or the gravitational force, pulling us down. Call that mg. Okay. And now here's where we have to be really careful, because we also have ball C underneath us, right? So ball C is underneath ball B. So we're also going to have, and it's not directly in contact with ball C, but it's attached by this string. So it is in fact the tension of ball C on B that is going to be also pulling down on ball B. So we're not just going to have gravity pulling down in this case, we'll also have some tension. So tension of ball C on ball B, TCB. Okay, now let's look at the electrical forces. Again, we're still having repulsion because they're the same charge. But in this case, instead of the electric force pointing down, because now we're above ball C, the electrical propulsion will point upwards. So we'll have the electrical propulsion pointing upwards. And we still have tension to contend with between A and B. Okay, so the tension of point A on point B. Okay, so in this case we have those four forces acting on object B. That is your free body diagram. Again, I'm not sure about the exact magnitude of each vector. I've drawn them all about the same. Are they all the same? Well, no. But we do still know that all four of these vectors will have to cancel out to give you a net force of 0, because we're still in equilibrium. We are still suspended from the ceiling. No acceleration. Okay, moving on to part D. Sigma F in the y-axis is still equal to MAY, which is still equal to, like I said, 0 meters per second squared, because we are in equilibrium. Now let's look at all the forces that are pointing upwards, the positive forces. So now the electric force is a positive force. The tension force, AB, is a positive force. Tension force, CB, is now a downward negative force. And gravity is still a downward force, all equal to 0. Okay, we've got our setup there. Those are the forces acting on the object in the y direction. Now, we want to isolate. What is the question asking us to find? Find the tension in AB. So we're going to have to isolate TAB. Solve for TAB. So you have mg plus TCB minus FE. Okay, now here's the part where before I plug my numbers in, I like to make sure that I plug in as specific of an equation for each term that I possibly can. So we have mg for the weight or the gravitational force. TCB, well, I don't really have an equation, but we did calculate that last time. I'm going to leave that alone. We know the electric force will be K Q squared over R squared, again because the charges are the same. Now here's where I want to get a little bit crafty. Now, of course, I could just plug in the number that I got from TBC last time, because the magnitude of TCB and TBC would be the same. But what I want to do here makes my life actually a little bit easier is if you remember from last time, TBC was equal to KQ squared over R squared plus mg. And again, that's what it was before we plugged numbers in. So what I'm going to do here, I am going to plug in that entire equation in for TCB, and some nice things will happen that'll make our lives a little bit easier. So KQ squared plus mg, okay. Okay, so I hope you see what I did there. mg is still mg. TCB was the equation that we saw for last time before we plugged numbers in, and the electric force is still KQ squared over R squared over here. Now this equation will simplify a great deal, because if you look, we have KQ squared over R squared minus KQ squared over R squared. So all the electrical force, actually in this case, we don't have to worry about it. Okay, it completely cancels. So we find that TAB is equal to twice mg, because we have mg plus mg becomes 2mg. which makes it very easy to calculate, saves you a lot of time in your calculator, and really reduces the chance that you'll make a mistake inputting a number. 2 times 0.005 kilograms times 9.81 9.81 times 10 to the minus 3 newtons of tension, which is also the same thing as 9.81 millinewtons. Okay, that's it for parts A through D. Part E, I'm going to let you try on your own. You use exactly the same concepts and principles for how to solve it as we did for all the other parts. The answers are online. You can look it up. I trust that if you're careful, you look at all your forces, you set up your free body diagram, you use Newton's second law, you'll figure it out. I hope you found that helpful. Thank you for watching.